This recording is an introduction to neurophysiology. We're going to be discussing some principles having to do with electricity, to make it a little bit easier for you to understand the principles of how neurons communicate. Because the neurons, as part of our nervous system, have a means of communication, and it does so by using electrochemical signals. So we're going to use principles of electricity to illustrate kind of how our nervous system works. I'm pretty much going to only do kind of like an overview of membrane potential and kind of principles of how we can allow different ions to move across the membranes. In class, we'll discuss things like graded potentials and action potentials and what happens at synapses and how we process information. So this is more of an overview to make it a little bit easier for understand what we're going to discuss in class. So let's talk first about the principles of electricity. So if you look at the picture on the right, we have a 12-volt battery. So the battery, what you have is at one end of the battery, you have an anode, which is the negatively charged end here, the negative here. This is the cathode. And what we have in a battery is kind of these electrons. And if we complete a circuit with this battery, we'll have electrons flowing from the anode to the cathode. And we'll be able to do some work. But just the battery itself, before we complete the circuit, we have what we call potential energy. And a measure of potential energy is voltage. What you see here is the 12-volt battery. So measure of potential energy is voltage. Now it's measured between 2 points that you see here, this positive end and this negative end. And they refer to that as potential difference. What potential do we have? How much difference in potential do we have to do work? So potential difference. Now, if we allow current to flow, we complete a circuit. Like if you go, let's look at the pictures on the left, is you have a lamp plugged into the wall. It's 124 or 120 volts, but the circuit's not completed because we have the switch off. But if you turn on the switch, you will allow the electrons to flow, and you have current flowing. And the current is the flow of electrical charge from one point to the other. So here we're having these electrons flowing. Now the amount of charge that flows is going to depend on voltage, because that's the potential to do work. The greater the voltage, the greater the amount of current flow. The resistance is think of resistance, it's going to try to impede that flow. So more resistance, you would actually have less current flowing. Now there is a law that we can use, and we're going to be applying it to our nervous system, is it shows you a relationship between the voltage and the current and the resistance. And this is Ohm's law right here. Is current, the abbreviation for current is the I, which you see over here. That is directly proportional to voltage. So you'll notice voltage is on the numerator. So in other words, the greater the voltage, the greater the current. So you more voltage, you complete that circuit, you're going to have a lot more current flowing. You'll also know, as part of the equation, resistance is on the denominator. So that tells you current is inversely proportional to resistance. So what you see here. In other words, this is what it means, is the greater the resistance, the less the current. Okay, so you see on the picture here, got a hand that's trying to prevent these electrons from moving. Now we can actually apply these principles to our nervous system. So in our body, give me a second. Our body, we're a big bucket of water with a lot of ions. The solutions in our body are ionic solutions. They have things like sodium, potassium. So our intercellular fluid, which is ICF, our extracellular fluid, which is ECF, are ionic solutions. And therefore, they can conduct electricity. Now, the voltage, that potential difference, that potential to do work, is related to our membrane potentials. And we're going to review our resting membrane potential. The resistance is provided by our cell membrane. So remember, the cell membrane is selectively permeable. The way it's set up is it does not easily allow charged things to move across. So that's going to provide resistance. But I had said it's selectively permeable. That resistance can be altered depending on whether or not we open or close certain types of channels. So again, the membrane has the ion channels. That's going to be the resistor. Resistance is going to be smaller if we have a lot more channels open. And if you open up channels, we're going to have ions move across. And the ions moving across will be our current. The voltage, the potential to do work, is derived from our membrane potentials, our difference between ions across the membrane. So therefore, that Ohm's law predicts how much current would flow when ion channels are open. And if we knew the membrane potential, that voltage across the membrane and resistance to pass, and if we knew that in the passage or the resistance to the passage of ions. So what I want to do is let's review a little bit of that resting membrane potential. We've introduced you to this in an earlier lecture when we talked about transport mechanisms. Understanding transport mechanisms is also very important in being able to understand neurophysiology, because ions are going to want to move from high concentration to low concentration, so knowing differences there is going to be important. So as a reminder, the cell membrane is selectively permeable, and it actually is slightly more permeable to potassium ions. So you'll notice on the picture, you see this leak channel. Leak channels mean they're always open. Well, we have a lot more potassium leak channels in cell membranes than we do sodium. So, and we have differences in ionic concentrations from the extracellular fluid and the intercellular fluid. And what you need to remember, this is going to be very important initially to remember, is you have a lot more sodium ions, which you see in the orange. You have, not orange, in the kind of purplish with the positive. You have a lot more sodium in the extracellular fluid. We have a lot more potassium in the intracellular fluid. There's a little more chloride in the extracellular fluid, and initially that's not going to be important for us, but it'll be important later when we discuss inhibitory interneurons or inhibitory neurotransmitters. But we have a different distribution of various ions across the membrane. So we got more chloride outside, we have more sodium outside. Inside you have a lot more potassium, but you have a lot of these negatively charged proteins. And what ends up being a result of this is we have an unequal distribution of charges across the cell membrane. And you'll notice you see all these negative charges here along the inside of the membrane. And so the membrane potential, and say at resting membrane potential, it is about, in neurons, about minus 70 millivolts. We don't do voltage, we do millivolts. So 1,000 millivolts is a volt. So this represents your potential difference. So the potential difference is minus 70 millivolts in a neuron. So it's negative because it's more negative inside the cell than it is outside. And in order for us to communicate, our nervous system to communicate, what we're going to need to do is we need to disrupt this resting membrane potential. And the way we're going to do it is we're going to open certain or close certain channels, which can allow movement of ions to move across, and it can disrupt that membrane potential. So this resistance can change because we can change the channels, what type of channels are opened or not. And so also I just run a little quick reminder about that sodium potassium pump. Actually, before I kind of go over that sodium potassium pump, I want for you to realize, as long as you initially know this unequal distribution, that you have a lot more sodium outside and a lot more potassium inside. So we have these gradients. So the intracellular potassium is high, and that's going to tend to want to move potassium out of the cell. So if you open up channels, it's going to want to leave the cell. The extracellular sodium is high. Therefore, it's going to have a tendency to want to move it into the cell if you open up channels. Those are passive chemical gradients. We're going to talk about electrical gradients when we talk about action potentials. But remember, positive charges are going to be attracted towards negative charges. So I just want you to keep that in mind a little bit later. Now, the sodium-potassium pump, which you see right here in the center. Well, the sodium-potassium pump is going to pump 3 sodiums out of the cell for every 2 potassiums that enter. And its job, the sodium-potassium pump, or the sodium-potassium ATPase, is going to be important in maintaining the resting membrane potential, keeping it about minus 70 millivolts. It's going to be very, very important when we talk about action potentials, in which we're going to be disrupting these differences across the membrane. This sodium-potassium pump is going to be important in kind of restoring this unequal distribution of ions, so that if we want to disturb the membrane again to send another signal, the sodium-potassium pump is going to be needed to do this. And remember, the sodium-potassium pump is an active transporter. It requires the expenditure of energy, hydrolysis of ATP, to do that pumping of the sodium out in exchange for 2 potassiums in. Okay, so we'll be looking at that in class, or discussing that in class. Now, one thing I wanted to show you is I had mentioned chemical gradient and electrical gradient. So if you look in this picture, what the arrows represent, they're like vectors, is where it's pointing, telling you what direction the ion wants to go. How big it is tells you how great it wants to move in that particular direction. So what you'll see at the top picture, it shows you the chemical gradient for potassium. So remember, potassium is very highly concentrated inside the cell. It really, really wants to leave the cell. So you see this big arrow, I'm going to change it to red, that's saying, okay, potassium really, really wants to leave. But we have an electrical gradient for potassium, because the negative charge inside the cells, potassium's like, well, I like to come back in because you have this negative charge inside the cell. But what we end up doing is we end up getting what we refer to as a net electrochemical gradient. We're going to do math. This wants to leave, this wants to come in. This is what we end up with. That represents your net electrical chemical gradient for potassium. It overall wants to leave the cell. Okay. The bottom picture shows you the same thing in regards to sodium. The sodium is highly concentrated outside the cell, so it really wants to come inside the cell. So you see it right here. But also, sodium wants to come in because there's a favorable electrical gradient. Positives want to go where it's negative. So they kind of add up together, and you get this really big looking vector that shows you the net electrical chemical gradient for sodium. That's going to be very important. So overall, so far, potassium wants to leave the cell, sodium wants to come in. But in order for these to do this, you're going to have to allow that membrane to be permeable to those ions. So we haven't discussed those yet. Now here's a term that I want to talk about, something called equilibrium potential. The equilibrium potential is the point where the electrical and chemical forces balance each other. It's kind of, what word I want to use. It's something that in real life doesn't happen, because you'd be dead if this happened. But if they've done this in the laboratory setting, is that they allowed a membrane to be freely permeable to potassium. For example, you see on the top. That's where the chemical gradient is equal to the electrical gradient. And what they did when they did this in the laboratory setting, they noticed that the membrane potential was minus 90 millivolts. And if you notice, it's pretty close to resting membrane potential. So big key thing to realize is that since that resting membrane potential is so close to the equilibrium potential for potassium, potassium plays a very important role in determining the magnitude of your resting membrane potential. So that's going to be very key, is the movement of potassium plays a very important role in resting membrane potential. But also remember, I mentioned earlier, the resting cell is a little bit more permeable to potassium. Now, under normal conditions, it's about minus 70 millivolts. That can change if we have disruptions in your ionic concentrations in your body, but we're not going to go into that. Now, if you notice at the bottom, they did the same thing for sodium. So in a laboratory setting, they allowed this membrane to be freely permeable to sodium. And so the point where the chemical and the electrical gradients for sodium balance each other, they noticed the membrane potential was about plus 66 millivolts. Now notice that's like 130 millivolts away from resting membrane potential. So the key thing to come with that is it says the diffusion of sodium is going to play a very important role in determining the rate of development and the extent of action potentials. So you see this big arrow coming in. So sodium, the movement of sodium across cell membranes is going to be crucial in action potentials. The potassium is more important in resting membrane potential because you have such a huge driving force for sodium. And you always think about, when we talk about diffusion, the rate of diffusion is going to be greater with the greater the difference, the concentration difference. And so we have a huge concentration difference for sodium. That's going to play a much more important role in action potentials. So that's something I want you to remember. So how can we change membrane potentials? I had mentioned that the way we're going to communicate is we're going to disrupt that membrane potential. Somehow we have to generate one. We're going to be talking about action potentials in order to get the information down axons, down the neurons, eventually to where we need it to go. So how do we do that? So remember, I had mentioned the plasma membrane is semipermeable or selectively permeable. You have this phospholipid bilayer, which does not allow ions to move across very easily. So we have channels. And so he says, you have an appointment. And we have to have channels specific for each type of ion. And the number of channels and whether they're open or not will determine whether or not these ions are going to move across. And so we have, remember, we have this unequal distribution of ions across the membrane, and you have that resting membrane potential. So how can we disrupt it? What are we going to do with these different types of channels that we have in the membrane? We have different types of channels. So let's kind of go over it. Now I want you to think of the channels as being different doors. So we'll say this door is for sodium, and this door is for potassium, and this is for chloride. So we have different types of doors. Now, how do we open a door? Well, we have to turn the knob, but sometimes they're locked. And so we have to have different types of keys. So my analogy is the channels are doors. The different keys are going to open the door. And so what kind of keys do we have? What type of channels do we have? So, and also to keep in mind is remember your principles of passive transport. You open a door, the ion's going to want to go from its high concentration to low. Okay, so keep that in mind. So we have leak channels. So leak channels means they're already open, always open, I should say. And I had mentioned that we have a lot more potassium leak channels. The sodium ones pretty much don't have many of those. And so we have a little bit more of the potassium leak channels. Then we have these ones that are referred to as ligand-gated. Some will say chemically gated channels. So a ligand, think of its example would be a neurotransmitter like acetylcholine. So you see here acetylcholine. So ligand means, it's from a word ligare, like to tie to. So if acetylcholine binds to this particular receptor, it activates it. What so happens in this example, this ligand-gated channel is a sodium channel. So if acetylcholine binds to it, the channel opens, you see here, and then the ion is going to move from its high concentration to low. So we have these ligand-gated channels. So they bind to certain neurotransmitters. Well, we also have channels that we refer to as voltage-gated. So they change in regards to changes in membrane voltage. And I want to introduce you to the voltage-gated sodium channels, since they're going to play a very important role in action potentials. And it just so happens with the voltage-gated sodium channels, we have different gates. We have this activation gate you see here. It's closer to the extracellular fluid side, the extracellular side of the cell. And we have this inactivation gate. Well, these voltage-gated sodium channels can exist in multiple forms. So at resting membrane potential, it's closed. And it's closed because the activation gate's closed. Inactivation gate's open, but I want you to think the ions are not going to move across if both doors are not open. So, but this activation gate is capable of opening, but it has to be at a certain membrane voltage for it to open. Another configuration that channel could be in is it's open. So the activation gate's open, so at a certain membrane voltage, it's going to unlock that door, and then sodium is going to move across. So that's a second configuration. Third configuration, is it's the activation gate's open, but this inactivation gate is closed. So this channel is referred to as being inactive. And again, at a certain membrane voltage, this inactivation gate swung closed. So sodium can no longer enter the cell. So that's another configuration that it can be in. So I want you to think of it as a door that has like a storm door and a regular door. Both doors need to be open in order for the things to move across. So I was able to find at least a couple of scenarios to kind of give you an example of these activation and inactivation gate. So here you're inside the house. This here is your activation gate. I'm just going to activation gate. And this one is your inactivation gate. So that's at resting membrane potential. No one's coming in because the activation gate's closed. Now the second picture, we're now looking from the outside. So here, this is the activation gate right there. This is the inactivation gate, but no one still can come in because both doors need to be open. So this is where we have the voltage-gated sodium channel is being inactive. I couldn't get a picture, couldn't find a picture on the internet, you think I would, where both doors are open. That's when sodium can move across. That's the only time sodium's going to move across. Now these gates will be open or closed depending upon membrane voltage. So those are the keys. So we have different types of channels. We'll talk about a voltage-gated potassium channel in class. It does not have an inactivation or activation gate, or it has just an activation gate. It's either doesn't have two gates to it. So we'll talk about that in class. So I want you just to kind of have a basic background in what we can do to open or close certain doors. And what we're going to do is we're going to walk through in class what happens if I say I open a ligand-gated sodium channel. What direction does the ions want to move? What's going to happen to membrane potential? That's what we're going to discuss in class. So we'll do that in class, and we'll start talking about graded potentials before we look at something called action potentials.